So what we're going over now is energy and work. So let's look at various forms of energy. So, nature of energy. You can hear energy as sound, you can see energy as light, you can feel energy as wind. Energy is all around you. You can use energy when you hit a softball, whenever you lift a book bag, whenever you compress a spring. Living organisms need energy for growth and movement. The nature of energy is not that important. This is a brief introduction. Energy is involved when a bird flies, a bomb explodes, rain falls from the sky, electricity flows in a wire. Uh, the 22nd. What is energy that can be involved in so many different activities? So here's the definition of energy. Nicole, you mind closing the door? Energy can be defined as the ability to do work. Here later, I'll actually define more precisely what energy is and what work means, but these two words, energy and work, have mathematical definitions. So energy can be defined as the ability to do work. If an object or organism does work, it exerts a force over a distance to move an object. Then the object or organism uses energy. So energy is defined as the ability to work. Work is whenever, so you do work whenever you exert a force over a distance. That's the actual equation for work. Work is equal to force times distance. Thomas, put your mask on. So because of the direct connection between energy and work, energy is measured in the same unit as work, called joules. So when we do energy or when we do work, our unit is going to be in joules. As long as our mass is in kilograms, or distance is in meters, or time is in seconds, or acceleration is in meters per second squared, and so on. So in addition to using energy to do work, objects gain energy because work is being done on them. So for example, if you were to take a box and you do some work on it by lifting it to the top of the building, it gains some energy. If you let go of it, it could fall back down to the ground. So you're giving it some energy, and then when you release it, it'll fall back down. Another thing is if you pull a rubber band, you're applying a force over a distance. So you're giving some energy to the rubber band, and if you let go, that energy will be released, causing the rubber band to snap or move. Michael, keep your mask on. So there are 5 main forms of energy: heat, chemical, electromagnet, magnet, nuclear, and mechanical. Broadly speaking, there's really only 2 forms of energy: kinetic energy and potential energy. But here are 5 more specific forms of energy. Would be probably mechanical can be broken up into kinetic and potential. We'll get into it here in a little bit. If I go too fast, you can tell me to go back. So heat energy is the eternal motion of the atoms. So the eternal motion of the atoms is called heat energy because moving particles produce heat. Heat energy can also be produced by friction, and heat energy causes changes in temperature and phases of any form of matter. So if you didn't know this, the temperature of an object is related to the motion of the particles. If the particles start moving faster, we would detect this by an increase in temperature. Particles tend to jiggle around, so even if you had like a block of iron, the iron atoms actually jiggle back and forth, so they're constantly vibrating and moving. How much they vibrate or bounce back and forth determines their temperature. So, yes, eventually you'll heat it up. So, in a solid, the atoms can't really move, but they can vibrate back and forth. They try to pull away, and then all of a sudden they get pulled back together. So, in a solid, the atoms can't really move, but they can vibrate back and forth. And how much they're vibrating causes the temperature. If they start vibrating really, really fast, so if they start vibrating really, really fast, they might be able to start sliding past each other. So, and if you had a block of iron and you heat it up to a really high temperature, the atoms could actually start sliding past each other, causing it to turn into a liquid. If you keep heating it up very, very high temperatures, eventually the atoms will be able to fly off and turn into a gas. Yes. So we also have chemical energy. Chemical energy is required to bond atoms together, and when bonds are broken, energy is released. So in order to keep atoms connected together in a molecule, for example, water is H2O. It has 2 hydrogens and oxygen bonded together. It requires energies to keep the atoms together. So you have to put in energy in order for it to actually come together. Otherwise, you just have hydrogen and oxygen gas. So if you were to burn hydrogen, add energy to it, and oxygen, the fire will actually cause hydrogen to bind together with oxygen to make water. If you were to rip apart the bonds, energy is also released. So you might have seen what happens whenever you take vinegar and baking soda together. It starts getting hot and creating bubbles. What's happening is they are reacting together and the bonds are breaking, producing CO2 gas, and it produces energy as a form of heat. So chemical energy is being converted into heat energy. Fuel and food are forms of stored chemical energy. So our body requires chemical energy to work. We get this from food. Particularly, we get this from glucose, and our body makes something called ATP. You ever had a biology class? Next, we have electromagnetic energy. So power lines carry electromagnetic energy into your home in the form of electricity. So electromagnetic energy includes electricity, includes magnets. If you didn't know, electromagnetism also includes light. Light is a form of electromagnetism, or electromagnetic energy. Each color of light represents a different amount of energy. So violet has the most energy, red has the least energy. So it's just based on the wavelength of the light. As the wavelength, or as the frequency of light increases, the energy increases. Very powerful electromagnetic waves, such as X-rays and gamma rays, have lots of energy, whereas radio waves have little energy. That's the reason why we use radio waves to communicate, because it doesn't use too much energy to send it across the world. And we got nuclear energy. Nuclear energy, so the nucleus of an atom is a source of nuclear energy. In order to get the protons, so if y'all know this, protons are positive, and positive charges like to repel each other. So if you put two positive charges together, they want to pull each other apart. However, there's something called the nuclear strong force, what pulls them together. So there's actually energy trapped inside the atom, holding the nucleus together. You might have heard of a nuclear bomb or splitting the atom. If you were to break this bond and break some of the protons off, it will release energy. It actually releases quite a bit of energy. If you do enough times, you get a nuclear bomb. So when the nucleus splits, this is called fission. Nuclear energy is released in the form of heat and light energy. Nuclear energy is also released when nuclear collide at high speed and join together and fuse. You don't really need to know this, but technically, if you fuse together atoms lighter than iron, it releases energy, and if atoms heavier than iron break apart, it also releases energy. That's really advanced stuff, but the reason for this is iron and nickel are both the two most stable atoms in the universe. So everything wants to become iron or nickel. Generally, it prefers iron, though nickel is technically slightly more stable than iron. So the sun's energy is produced from nuclear fusion. It's a reaction in which hydrogen nuclei fuse together to make helium nuclei. So you take one proton and another proton, they combine together with two neutrons to make a helium nuclei. Again, I get these PowerPoints online. This statement obviously isn't true for us, but whoever I got these PowerPoints from, they actually live next to a nuclear power plant. Nuclear energy is the most concentrated form of energy. So in a glass of water, if you could magically do fusion on the hydrogen in the water molecules, fuse all the hydrogen into helium, a single cup of water has enough power to fuel a city for several years, or the entire United States for I think a day or something. It has a single cup of water has enough nuclear energy to power Broadus for hundreds of years. Because you're not breaking the bond and put your mask on, Michael. You can't break so it takes a lot of energy. You have to put in a lot of energy in order to break these bonds. So the reason why the sun does it is because gravity is really compressing the hydrogen gas. So we have a really dense star pulling very strongly and causing them to be pulled closer to the core of the sun. We also have it's very hot. So again, remember I said heat and temperature is the speed at which they move. So the sun is very, very hot. So the atoms of hydrogen inside the sun are moving at crazy high speeds. And then we have mechanical energy. When work is done to an object, it acquires energy. The energy it acquires is known as mechanical energy. So, for example, when you kick a football, you give mechanical energy to the football, making it move. So you're applying some work onto the football, thus increasing its energy by making it move. When you throw a bowling ball, which that's misspelled, you give it energy. When that bowling ball hits the pin, some of the energy is transferred to the pins. Also transfer momentum. So remember that I talked about earlier about momentum. I said momentum is constant or is conserved. We also have energy conversion. So energy is also conserved. It stays constant. Energy can be changed from one form to another. Changes in form of energy are called energy conversions. But energy cannot be created or destroyed. You can only transfer it from one object to another. So you can take some electrical energy, send it through a heater, and convert electricity into heat energy and heat up a house. You can burn some coal or some wood and convert some of the chemical energy into thermal or heat energy. All forms of energy can be converted into other forms. The sun's energy through solar cells can be converted directly into electricity. So converting the electromagnetic waves into electricity. Green plants convert the sun's energy, electromagnetic, into starches and sugars, which is chemical energy. Michael, keep your mask up. Not Michael. Thomas, keep your mask up over your mouth. If I go too fast, tell me. So other energy conversions, for example, an electric motor, electromagnetic energy is converted into mechanical energy. In a battery, chemical energy is converted into electromagnetic energy. And mechanical energy, such as in a waterfall, can be converted into electrical energy in a generator. Question: a hair dryer. What do you think? What energy do you think it converts into what other energy? All right. Last year, students put nuclear energy. Yeah. Another thing for heat energy is thermal. You'll see me use both of them. Instead of saying heat energy, I usually call it thermal energy. So, an automobile energy, in an automobile engine, fuel is burned to convert chemical energy into thermal or heat energy. The heat energy, in turn, is then converted into mechanical energy and pushes your car forward by rotating the tires. So technically, it turns it into rotation of the tires, and then a rotation of the tires pushes on the ground pushes back, and we go forward. So the chemical energy is used to heat up the gas, which causes the air inside the piston to expand, causing the piston to push up, and that in turn eventually turns the car wheels. So in a car engine, we go from chemical to heat and then mechanical. Yes. Yes. The most common energy conversions is a conversion between potential and kinetic energy. All forms of energy can either be potential or kinetic. So the true main forms of energy is just all boils down to kinetic and potential. They call it states of energy instead of forms of energy. So there's two states of energy. You can either be in kinetic or you can be in potential. Kinetic energy is the energy of motion. If something is moving, it has kinetic energy. Potential energy is energy that is stored. So, what do you think thermal or heat energy is? Is it a potential or is it a thermal? Or is it a kinetic or is it potential? Yes. Technically, temperature is the average kinetic energy of all the atoms. What do you think chemical is? Potential. It's stored in the bonds. Nothing is moving, or doesn't have to move when they're bonded together. Nuclear. What do you think nuclear is? Potential. Because it's stored in the nuclear bonds. So we also have like gravity. What do you think gravity is? Gravitational. Potential. So if I lift something up on top of the building, it's being stored as in the form of gravitational potential energy. And you running would be a form of kinetic energy. So the energy of motion is called kinetic energy. The faster an object moves, the more kinetic energy it has. What? Oh yeah. Also, the more mass you have, the more kinetic energy you also have when you're moving. So if two people were running at the exact same speed, the person with the more mass has more energy. So kinetic energy depends on both mass and velocity. So the equation, I don't like how it's written here. Kinetic energy is equal to 1/2 times mass times velocity squared. So the code word of the day is on the screen. So I prefer writing kinetic energy in this form. Kinetic energy is equal to 1/2 mv squared. So kinetic energy is equal to 1/2 mv squared. Yes. Here they put the 1/2 on bottom, or they move the 2 down. So, which one has a greater impact? If you increase the mass or if you increase the velocity? Velocity, because velocity is squared. So if I increase the mass from 2 to 4, I double the mass, right? So the kinetic energy would double. So doubling the mass doubles the kinetic energy. However, if I go from 2 meters per second to 4 meters per second, the kinetic energy is quadrupled because it's 2 squared. That would be momentum, half of momentum. So the square is only on the velocity. So we also have potential energy. Potential energy is stored energy, stored chemically in fuel, the nucleus of an atom, or in the chemical bonds in foods. Are stored because of the work done on it. So if you stretch a rubber band, you're going to be storing some potential energy. If you wind up a clock, you're going to be storing some potential energy. Pulling back on a bow's arrow. So when you pull back on a bow, you're adding some potential energy to the string. If you let go, it'll convert it into kinetic energy. Lifting a brick high up into the air, you're adding some gravitational potential energy. In this class, I only go over one type of potential energy because the equations for the other ones get somewhat advanced. Rubber band and spring isn't that advanced, but I only look at gravitational potential energy in this class. So gravitational potential energy is potential energy that is dependent on height. How far above Earth's surface are you? And this is called gravitational potential energy. So technically, it doesn't matter if you say that Earth's surface has 0 energy, or if you say it has 1,000,000 energy, or if you say it has 1,000,000,000. Technically, the only thing we're concerned with is changes of energy. So if you go, so if you had a box and it has 1,000,000 joules of energy, and you add 10 joules of energy, it would have 1,010,000 joules, right? So all you did was increase this energy by 10 joules. Versus if I had a box that was 50 joules and I added 10 joules of energy to it, it would go from 50 to 60. That's still a change of 10. So technically, if you were to ask for the total potential energy of an object, you would have to go look how much nuclear energy is in the protons, how much chemical energy is in all the bonds, how much gravitational potential energy from the sun, the Earth's core, from cars nearby. All of this doesn't really matter because we only concern ourselves with changes of energy. So we set some point to be 0. And usually we just arbitrarily set the surface of Earth, no matter where you're at, as the cutoff of 0 energy. So technically you would need to measure from the center of Earth, but it doesn't really matter because we only deal with changes of energy. For example, if you give some, so if you start at 10 meters high and you go down to 5 meters high, you've lost 5 meters. That means we can use some conversion factor and figure out how much energy was transferred from gravity into kinetic. Note that we didn't really care about the total energy, just a relative difference between those 2 points. It'll make more sense when we go into examples. So, energy that is stored due to being stretched or compressed is called elastic potential energy. So a spring, a rubber band, a bow, and you pull on the string of a bow, all these are examples of elastic potential energy. Again, we're mostly going to be focused more on gravitational potential energy. A waterfall, a suspension bridge, and a falling snowflake all have gravitational potential energy. So if you stand on a 3-meter diving board, you have 3 times the gravitational potential energy than you have on a 1-meter diving board. The bigger they are, the harder they fall is not just a saying. It's true. It's true. Objects with more mass have greater gravitational potential energy. By the way, they're writing it as GPE and they're putting periods. I write it as potential energy with a little G under it, a little subscript. It's down below. It's a subscript. I'll go ahead and write it. It's equal to mass times acceleration due to gravity times height above some point. We arbitrarily set 1 point to be 0 energy. Again, the math doesn't matter if we set it to be infinite or arbitrarily 1,000,000. We just define some height to be 0 energy. And it's just the surface of the Earth we define as being 0. The math still works even if it's different. So notice they define it here as gravitational potential energy is equal to weight times height. What's the equation for weight? What is weight? Force due to gravity. So that what is force equal to? M times A. Here I just replace A as the letter G. So we end up with what I wrote on a piece of paper, mgh. So weight is mass times acceleration due to gravity, which I write as m times g, and then we get height. Note that it's lowercase g for acceleration due to gravity. Capital G is the constant 6.67 times 10 to the negative 11, so on and so on. So, for example, roller coasters work because of energy that is built into the system. Initially, the cars are pulled up to the tallest hill, giving them a great deal of potential energy. From that point, the conversion between potential and kinetic energy powers the car through the entire ride. If you didn't know this, all they do is take a roller coaster, and you can hear it when they crank it up. They crank it up to a really high point, and then they just let it fall by itself. When it's actually going around all the loops and doing everything, there's nothing powering it but gravity. Gravity is causing it to go from potential energy into kinetic energy. So here we can see potential energy is being converted into kinetic energy. And kinetic energy goes back into potential energy. And we see that there's a balancing act. The total energy stays constant. So the green bar is total energy. So notice that if you add up the kinetic and the potential energy, the total energy doesn't change. All that's happening is potential energy is being converted into kinetic energy, and when it goes in the loop-de-loop, kinetic energy is being converted back into potential energy. So at the maximum point, it has the most potential energy and the minimum kinetic energy. When it reaches the lowest point, all the potential energy is converted into kinetic energy. So as a basketball player throws the ball into the air, various energy conversions take place. So when you first throw a basketball up into the air, you give it some kinetic energy. As it keeps getting higher and higher, that kinetic energy is going to convert into potential energy due to gravity. So eventually, if you throw a basketball straight up into the air, it'll eventually stop and start coming back down. So if you push it up, you give it some initial kinetic energy. Gravity is going to cause it to slow down because it's gaining potential energy until it reaches a point where it has no kinetic energy and only potential energy. On the way back down is losing potential energy. That potential energy is being converted into kinetic energy. Which gives us the law of conservation of energy. Energy can be neither created nor destroyed by ordinary means. It can only be converted from one form to another. If energy seems to disappear, then scientists look for it, leading to many important discoveries. This is actually how we've mostly been discovering new things, new particles. You might have heard of the Large Hadron Collider, where they smash together atoms at really crazy speeds. What they do is they'll look after they explode if any energy was lost. And if some energy was lost, that energy had to go somewhere. And what ends up happening is they discover a new particle, like the Higgs particle, which was recently discovered. So in 1905, Albert Einstein said that mass and energy can be converted into each other. He showed that if matter is destroyed, energy is created. And if energy is destroyed, mass is created. And it's related to the simplified equation, E equals mc squared. That's not the full equation. The full equation is more complicated. This is only works for an object that's not moving. Any questions? No. Hold on a math. Hold on a math. Are there any questions? I think this is going to be the most math intensive yet. That's it for later.